Hi, my name's Raj Joshi. I'm one of your physics teachers and I also work across the E21C Trust looking after science. I'm going to have a chat with you today about waves and then also give you some questions that you can discuss with your teachers. At different points during this video, I'll tell you to pause the session and then send some answers over to your teachers to have a discussion. When you send those answers, I want that to be a two-way discussion. So don't be too careful. If you think it's a particular answer but you're not 100% sure, that's fine. Send it anyway. If it turns out that it's wrong, your teacher can teach you what the right answer is. If you're in school this week, I hope that you enjoyed your sessions in science. Lockdown has been an interesting experience for all of us, and we've had a lot more free time than we're used to. During lockdown, I've been doing two things: growing my beard and listening to my extensive collection of country music. Here's a picture of me enjoying country gold hits. You can see at the top there's a CD. The music is stored on the CD. We've got a speaker there, and then you've got me having a great time, and the music is somehow going into my brain. How does it get there? We've got some sort of way, some sort of process, I guess you could call it, from getting from the CD into the speaker, into my ears, and then into my brain. What we're going to be thinking about today is the process from the speaker through into my ears. This is something that we think about when we talk about sound waves. But what's actually going on? How much do you already know? The speaker cone will vibrate. And we know that there are things inside our ears, things like eardrums, that also vibrate. But how does the sound get from the speaker into our eardrums? There are four pictures here. Each of them is a way of explaining how the sound gets there. One is, I suppose, a much better explanation, a much more correct explanation than the other. Have a think about which one you think explains how sound waves travel. Then pause the video and write to your teacher on Teams explaining which one you think is the best. Pause the video now and send that message to your teacher on Teams. I hope that you had an interesting conversation with your teacher about that previous example. Here's another one to have a look at. At the picture on the top, you've got an image of a speaker cone vibrating. Those little blue circles are particles in the atmosphere, and the sound wave is somehow getting transferred from the left of the screen to the right. There are four statements below it. Let me read them out to you. A. Air particles can be pushed forward by other air particles that hit them. B. Air particles vibrate and slowly move forward. C. Air particles can bounce backwards off the air particles they bump into. And D. Air particles move backwards and forwards over and over again. Some of these statements are correct, some of these statements are incorrect, and some of them are only half correct. Have a think about which ones are correct and which ones you don't really agree with. Then pause the video and tell your teacher. Pause the video now. There are lots of different types of waves. If we're in the classroom right now, I'm sure we could sit down and have a think about all the different types and make a list and write them on the board. Usually when we do this, these are the waves that students come up with. Sound waves, pressure waves, water waves. I'm thinking about things like ripples on the surface of a pond or the waves that you surf on. Light waves, microwaves, and we'll see there's quite a good link between light waves and microwaves later on in the course. And even things like Mexican waves that you might see in a football stadium. you can see that I've put them into two categories. The ones on the left we call longitudinal waves. The ones on the right we call transverse waves. Now, longitudinal waves are waves in which the vibration of the particles is parallel to the way that the wave transfers. For transverse waves, it's perpendicular, it's at right angles. Pause the video now and copy down the diagram and the definition at the bottom of the screen. There are a few technical terms in that explanation. Let's have a look at what they mean. So the first word I want to talk about is oscillation. So if something is oscillating, it's moving back and forth over and over again. So this is moving back and forth. This is oscillating. If something just moves back and forth once, that's not necessarily an oscillation. It needs to be happening over and over and over and over again. Let's have a look at a simulation of something that can oscillate. Here we've got a PhET simulation of things on a string oscillating up and down. Let's just pause it to have a look. These are sort of little beads. You can see these, some of them are green. They've been coloured in for us to understand it a bit better. Keep your eye on a green bead as I move the simulation forward step by step. How is that green bead moving? The green bead is just going up and down. So even though the wave is going to the right, the green bead is just going up and down. So this is a transverse wave. The oscillation of the particle is at right angles to the wave direction. We can change a few different things on this simulation. We've got the amplitude at the bottom here and the frequency. Let's get a ruler here. It says here the amplitude is 0.75 centimeters. What 0.75 is about here, so that is the maximum height of the wave. Let's see what happens if we bring it up to 1. Our amplitude is the highest the wave goes. If we go down to about 0.5 centimeter, there we go. Our amplitude here is 0.5 centimeter. Let's have a look at the frequency. So the frequency, it says here, is 1.50 hertz. Let's reduce the frequency. Okay, and let's go up a bit. So the frequency is how often this wave goes up and down. How many times per second? And this measurement, hertz, is the number of oscillations per second. So hertz is the number of oscillations per second. If you struggle to remember this term frequency, think of the term frequently. If we say the 119 comes a lot more frequently than the 194, that means that it happens many more times per hour. Frequency is how many times the wave goes up and down per second. We can also talk about the term wavelength. That's from one point on the wave to the adjacent point on the wave. The next one that's doing the same thing. So here we've got a peak to a peak, or the bottom, the trough to the trough of the wave. That's defined as the wavelength. Let's have a think about how the frequency and the wavelength affect each other. We can even do a little short experiment. Let's bring the frequency to, let's say 1. So the frequency is now on 1 Hertz. What's the wavelength? Let's get this lined up here. So from here, we're going to go to the next adjacent point. So that's here. That's about 6.1 centimeters. Let's type that in. So our wavelength is 6.1 centimeters. Now we want to do this really in meters. So let's take this value, 6.1, and divide it by 100 to work out the wavelength in meters. Ooh. Let's go up 1 and then let's have a go going down 1 as well. So let's go to 1.5. And pause it. So from here, all the way up, all the way down to our next one. 4.1, let's say. 4.1 centimeters. And that works out as 0.041 meters. And then let's go up 1 as well. Let's have a look at half a hertz. Let's go all the way down to half a hertz. So the frequency is going to be lower. It's going to be going up and down much slower. And let's see if we can stop it. Now the problem that we've got here is we don't actually get a whole wavelength onto our screen. So we're going to have to be a little bit smarter about this. It's going down here, and then we know if we were to carry it on, it would go up and down again. How are we going to deal with this? Well, what we can do is if we measure from here to here, that's what, 6.1? And then think about it. If it's 6.1 from here to here, then from here to the imaginary point there, when it comes back down again, it will be another 6.1 as well. So 6.1 plus 6.1 is 12.2. So let's put that in there, 12.2. We've got our wavelength up here. Here we go. So we've got 3 different wavelengths at 3 different frequencies. I finished them off earlier. And what we can also do is use this equation. Wave speed is the frequency times the wavelength. So I've multiplied the frequency times the wavelength to get a wave speed. And my average wave speed is 5.975, let's say 5.9 or 6 meters per second. In that explanation, I used quite a lot of different technical terms. I've got those keywords written on this slide. What I'd like you to do is to pause the video, copy down this table, and write the definitions of all those words. If there's anything that you missed, or I went over a little bit too quickly, it's recorded. So rewind the video and watch that section again. You can watch it a couple of times if you like, until you're able to write the definitions of these words. Pause the video now, copy the table, and if you need to, rewind the video to watch that section again. In that simulation, the speed of the wave moving across the screen was about 6 meters per second. Now, waves like light or sound travel at different speeds, a lot faster than that. Sound is pretty fast, but that sound wave does travel slower than a light wave. We see this often during a thunderstorm. Usually in a thunderstorm, you'll see a flash of lightning and then you'll hear the thunder afterwards. And if the thunderstorm is further away, there'll be a bigger gap between the two. Both the lightning and the thunder are generated at the same time. But because the speed of light is really, really quick, we see the flash of lightning almost instantaneously, almost just afterwards. Whereas the sound from the event, the thunder, takes a little bit more time to get to us. So sound travels at about 330 meters per second. It actually depends on things like the temperature, the density of air, even how wet it is outside. Whereas light travels much, much faster. It's about 1,000,000 times faster than the speed of sound. That's why we have a gap between the thunder and the lightning. I hope those explanations we went through made sense to you. If not, ask your teacher. As we all know, those GCSE exams are less than a year away now, so we need to start tying in our knowledge to GCSE exam questions. This is a real AQA exam question that I've put onto the slide. Have a read of it, pause the video, and try and work it out. Then send your answer to your teacher. They can discuss if you got the right answer or not, and if you got the wrong answer, they can explain the correct answer to you. And that's a fantastic way to learn. I'll leave you with this exam question and hand over to your teacher. Goodbye.